simplify some code. So in this problem, given to the matrix, starting from zero position, how many unique ways are there to get to the finish line? So if we take a look at this example right here, for 3 by 7, and there are 28 ways, distinct ways to get to finish line, and our robot can only move down and right. So can only move either down and right at any point. So this is a dynamic programming type of question, and the first thing, so in all dynamic programming questions, I think the hardest of work, the majority of work relies on coming up with that transition function. Once we have the transition function, the coding part is just straightforward. So first thing first, this our function is 2D, so I and j. What is our objective? Our objective is to find all number of possible paths can get to reach the bottom right corner. And let's come up with some base cases. So if we have 1 by 1 matrix, how many ways to get to the bottom right corner? There is one way. What about if we have 2 by 2 matrix? How many ways are there? So let's say 2 by 2 in here, and that's like this is our finish point. So we can move down and right. We can move right and down. So there are 2 ways. So etc. We can do all this type of base cases. So from here, we can try to come up with our transition function. So our transition function will be ij, and when we're coming up with our transition function, the best way to think about it is, let's assume that we are at the finish line already. So we are here, and how many ways are there to get to there? We can come from above, or we can come from its left side. And in this type of questions, when we are seeing or, it usually means just adding it, and this is a combinatoric type of question, so we're trying to get all the sums. So if we are already at finish line, because like that's what we're at right here, we are at the finish line, and how many ways we're coming from above, and we are coming from its left side. So from our row, we can come from here, and we can come from, so I is a row, and then j is our column. So from top, we're already here. So from above, when we're coming, we are just subtracting 1, and then when we are here from left side when we are coming, so this is our column, we're just like left side will be this one right here. So this is our transition function, and we can see this is a dynamic bottom-up dynamic programming. The reason is that we are relying on previous calculated solutions, and then we're coming up with our final solution. So our solution is this one right here. We will be returning this in the end. So since we have our transition function, let's code it up. So let's create our 2D matrix, and so M is our row, N is our column. And let's come up with our base case. So when there is just 0 by 0 matrix, there is only one way, and we're going until our M. We're going until our N j++. So if we take a look, we're starting from 0 indexes, and So when we are at 0, we might fall into a risk of having a -1, and when we're at 0 here, we might fall into a -1. So we need to filter it out. So only accept when these i's or j's are greater than 0. So we can filter that out. So we can say it's like if j is greater than 0 and I is greater than 0, then apply our formula here. So dp I and j dp. So I'm just copying our formula. I -1 and j plus dp I and j -1. So we are so I is our row and j is our column. So in here, only time when they are above, then we are using it above greater than 0, then we are updating it. So it will be cases in if we take a look at this matrix, when row is 0, then we need to update this column right here as well. So in this case, we can also say else if so j is our column. So if only j is above 0, because like if we don't do this once, like we'll be updating it in whenever j and I is greater than 0, when all those columns, like for instance the top one right here, will be left out, which will not result in accurate results. So so when I is 0, meaning that we are at this row right here, we need to still update our matrix with all those different movements here. So when only j is greater than 0, then we will be updating our matrix. So with this one right here, because this is responsible to updating the j side right here. And else if same thing goes for row as well. So you can just copy this one, and this is for our row. Okay, so once we do all that thing, like I was saying, this will be our result. So our result relies in here, because like we are starting at grid 0 and 0, and the result is in this one. Okay, let's run our code. Perfect. Let's submit it. So for time complexity, it's, as you can see, it's like we have inner loops. So first, the top one is O of, let's say O of m, where m is all elements in this row, and the inner one is O of n, where n is all elements in column. So time complexity is O m times n. For space complexity, it's the same way, O m times n, because we need extra space to store all those different type of movements in our matrix, and this is m is all those numbers in m and in row, and n is all those numbers in our n. So O m times n for space complexity and for time complexity.